Okay, so I'm going to talk about exponents with you. I'm going to assume that you know a little bit about exponents and have seen them before. But I'm just going to remind you of properties that exponents have, and we'll see some examples. So, for any real number, x not equal to 0, and power or exponent n, which is going to be a real number. This fancy r here, that means real number. We write x to the n, where x is the base of the exponent. Is the base of the exponent. And x to the n is read as follows. So you could read it in a couple different ways. You could read this as x to the power of n. You may also read this as x raised to the exponent or power n. Now, exponents really, when you deal with general real numbers, at first it's really kind of unintuitive what you do with them. I like to think of them like in terms of integers, because that's often what you're going to encounter. Intuitively, I did it. Intuitively, when exponent n is an integer, then you could think, then x to the n is equal to x times all products of x, and this is done n times. So you could just think of it like a repeated multiplication. That very much, when you think about it as repeated multiplication like this, it's very intuitive, and a lot of properties about exponents make a lot more sense when you want to first convince yourself of things. It's, as a remark, also, it's worth noting that we consider x to the 0, or the 0th power. This is equal to 1. And if ever I give you a negative exponent, like x raised to the minus n, this minus is just saying it's 1 over that thing with the exponent. Okay? So I'm going to give you some properties, and we're going to do some examples. So let's look at some properties. So let's talk about some properties that exponents have. So I'm going to let real numbers x and y not equal 0, and m and n be real numbers. So I'm going to assume these guys here, and let's proceed. So the first one I'm going to talk about is the product property. So a product property, quite simple. If I have two numbers that have the same base, but they're raised to different exponents, I could do the following thing. So if I have x raised to the m and x raised to the n, notice the same base on the exponents. If I have the same base, then I can sum over them. So if I have a product like this, the exponents add to one another like this. Just as an example, if I have 2 cubed times 2 squared, what should that be? 2 cubed times 2 squared. Well, by this product property, it should say that it's equal to what? It's equal to 2 to the power of 3 plus 2, which is 2 to the power of what? 2 to the power 5. What's 2 to the power 5? Anybody that knows powers of 2's? Let's see. 2. So 2 to the power 1 is 2. 2 squared, 4. 2 cubed, 8. 2 to the 4, 16. 2 to the 5, 32. Sure, if you're interested in computer science, you probably know your powers of 2 back of your hand, you know? Slap! Hey. Okay, so that's the product property. Let's talk about some more properties that exponents have. Okay, so the next one is the quotient property. If you're not sure what the word quotient means, it means you can think of it as division. Whoops, not quotient rule, quotient property. I'm getting ahead of myself. So I have the quotient property. Now, if you could see that in a product, it adds the exponents, you might guess what the quotient would do. So if I have x raised to the m over x raised to the n, what should happen? Well, it should be that it subtracts them. So it becomes a difference. Instead of a sum, it's a difference. So, just as an example, just again, because I like to be complete with you, is I give you 2 to the power of 10 over 2 to the power of 7. That's equal to 2 to the power of 10 minus 7, right? And that's 2 cubed, which I'm sure you know that that's equal to 8. Okay, another property. Now, this is where things are going to get a little bit fun. These ones I consider more interesting properties. I promise you, you will find these pretty interesting at some point. If you're doing some fancy algorithm analysis, every once in a while, some strange thing pops out where you're like, oh, well, why would I ever need this property? Sometimes it creeps into your analysis every once in a blue moon. This is one of them. Okay, so if I give you x raised to the m, and I have all of this. Now remember, this is in parentheses. And if this is all raised to the n, this is equal to x raised to the product of m and n. So it's not a sum like this. It's because it's being raised again to another power. So just as an example, if I have 2 to the power, so I have 2 squared like this, raised to another power of 5 like that, then this is 2 to the power of 2 times 5, which is 2 to the power of 10. Now for your pros that know all your powers of 2, I'm sure you just know that this is going to be 1024. Bam, bam. You see? See, I'm getting really excited here. Okay, another one. Power of a product property. So power of a product property. So this is one that it oftentimes doesn't get enough love, and sometimes it does pop up in some of the proofs if you're trying to prove some of these properties. So let me show you what this is. This is quite simply stated as follows. So if I have x times y like this, so just a product, and I raise this to the power of m, it actually decomposes over the product here. So it becomes x to the m times y to the m. Now, one thing I must point out is remember that these do not have the same base. So notice this isn't the exact same as the product property I had over there. This is in fact a little different. So just as an example, if I have 3 times 2 squared, all squared, this is just 3 squared times 2 squared, which is just 9 times 4, which is equal to 36. Bam. Now, you might ask, Dan, how do I know that that property makes any sense? Well, think about it. If this is x, so just, I want you to first think about if the power was an integer. It's going to be x times y times x times y times x times y. How many times? M times. So if you think about it more like that, you can actually rearrange all the powers that you have. So how many times do you multiply x? You multiplied m times. How many times do you multiply y? M times. See? Nice and easy. Okay. Believe it or not, that's all I have to really say about exponents. So hopefully you had a little bit of fun with this. So we're going to move on to talking about its cousin, its inverse, the so-called logarithms. So let's talk about logarithms. Let's talk about logarithms. So I'm going to define first what a logarithm is. Let there be positive real numbers b, x, and y, where b is not equal to 1. So it's worth noting that exponentiation and logarithms are very closely related. So we write b to the y is equal to x if and only if, now just as a reminder, if and only if you read something on this side, whatever I write over here, they are going to be logically equivalent. As in, if this is the case, then this is the case. If that's not the case, then this isn't the case. Clear? Okay, so so if I have these right here, if and only if, I'm going to write it as log base b of x is equal to y. So this right here is called the base of the logarithm. And I'll give you a very basic intuition of why exactly you might find this definition a little strange at first. And then it actually makes a little more sense. Okay, so imagine I give you the base of exponent, hence the b, base of the exponent. Get it? Get it? So base of that, base of that. Okay, you want to think about it more like a game. So if I have b to the y is equal to x, I want you to imagine I give you x. I give you x right here, and I tell you the base of my exponent. I want to know what power you raised b to get x. So it's in fact in the inverse of exponentiation. So in this, I raised the power of y to get x. Here, I have b, and I have the result of b to the y. I want to know what exponent you raised it to. So these are closely related. If you know one of them, then you know the other one. So very often, knowing this, so oftentimes you'll find that this definition of the logarithm will sometimes creep into things you're doing where it's very unclear, like, okay, I have this logarithmic term. What does that mean? Well, remember, this is the definition of a logarithm. Okay? So actually, just to make sure I'm really clear what I mean by this, let me just do a quick example. So imagine I give you 2 cubed. What is 2 cubed? We already established that's 8, right? What is that in the logarithm world? Well, the base of the exponent is 2, so it's log base 2. And what's x? X is the result here. Log base 2 of 8. Well, think about it. Remember, what is the exponent I raised 2 to get 8? It's 3, right? Notice that it's really not that tough. At first, it's a little strange when you look at it because, okay, well, I'm not used to thinking about things backwards like that. It's because it's an inverse operation. So that being said, when you think of an exponent, it shoots up like this. However, a logarithm does, instead of shooting up like this, it curves like this, but it curves slowly. So oftentimes when we do like algorithm analysis, sometimes you find that if you kind of come across an algorithm that has logarithmic properties like that look like something more like this, where it's like where n, like the input, has something to do with it. Usually that's a desirable characteristic of a running time of an algorithm because the growth rate of such a function is very slow. So this is in contrast to something like a linear term. Okay, so let me make some notes here. So logarithms have different bases. As you can clearly see, I can pick what the base is. So some common bases include the following. So here are some common bases. So the first one I want to mention is that is base E. You might know this constant. This is approximately equal to 2.71828. If my memory serves me correctly, I'm trying to do this off the top of my head. So whether it's E, you might know this constant. You might know this as if we have this base, it's often known as the natural logarithm. Sometimes written as ln of n, where n is the input. Another common one is the base 2. This one's very common in computer science circles. Oftentimes when you talk to computer scientists, if they just write log n like this, they're often assuming that it's log base 2 of n. Not always, but very often. In general circles, you'll often find that they assume base 10. But in computer science circles, usually will find that people tend to assume the binary logarithm. So this is often called the binary logarithm. Oftentimes, this logarithm sort of melted in the microwave again. Oops. So this is called the binary logarithm, and I'll say it's common in computer science. Oftentimes pops up in algorithm analysis all over the place, whether it be talking about representations of information like bits or information theory, all sorts of fun things, like even ranging from wild things like entropy. So I want to remark, just because I like to bring up things that aren't as common, some people use the notation LB of n. I don't see it very often, but I feel like I need to mention it. So you won't find me usually using that notation, but I feel like I need to acknowledge that it exists out there. So you ever see LB of n? That usually is the binary logarithm. But just you won't see me using it very often. So I'm going to talk about some properties of logarithms. Now, you're going to find I'm not going to do a lot of examples with these because you will see plenty if you start playing around with logarithms. And that, like I said, logarithms and exponents are closely related. Hence, you're going to find that all the examples I gave, I encourage you to try them with logarithms. Here are some properties. Here's some properties of logarithms. So the first one is the so-called product rule of logarithms. So you're going to find that there's going to be a natural analogy to almost everything I've shown you before. Almost everything. So if I give you log base b of x times y, so a product like this, what happened when I had my exponents? When I thought about exponents where I had x to the m times x to the n, what happened? The exponents added to each other, right? But remember, in a logarithm, what are we talking about when we talk about what log base 2 of something is? It's the exponent, right? So it's quite natural that the outcome of this should be that they add to one another. So you could split a product into two sums. Is that nice? Naturally, think of a quotient rule as you might guess it. I'll let you think about it. Is it going to be that it adds them, or it's a difference? It's a difference. So we have log base b of x over y. This should be, instead of a sum, it is a difference. Not a plus, a minus. Okay, so we have the quotient rule. Now, intuitively, I told you that the product rule is where I add over products. So imagine I had a bunch of products over each other over and over again, like an exponent. Just like imagine if it was an integer power. What should happen? I should have a bunch of sums, right? And if I have a bunch of sums that look exactly the same, I can factor them into some term. So for example, if I had a power of 3, like say if I had 3 terms here, you would agree with I have three terms in a sum, right? Well, this is going to be a nice generalization of that. It's called the power rule of logarithms. So if I give you log base b of x to the y, you could drag this y out in front, and then I end up with log base b of x. So it's going to be y times log base b of x. It's worth noting, remember, these are all equalities, so you can rearrange them back and forth. So if you really don't like a constant in front of your logarithm, you can drag it up as an exponent, and vice versa. So keep that in mind. Finally, one last one I need to point out is the change of base formula. So suppose you have a logarithm and you really don't like the base of your logarithm. You want it to look like something else. Like say if you have something that's in base 10 and you want to convert it to base 2. There is actually a nice relationship that logarithms have, so you could switch the base. So if I give you 2 valid bases, a and b, log base a of x is equal to log base b of x over log base b of a. So if I want to convert from a to b, notice I introduced this constant term right here. So notice they differ by a constant. You'll find that the power rule and the change of base formula tend to be very often something that will creep into big O proofs, for example, when it comes to dealing with logarithms. I find generally these two are the ones you're going to run into very often. Not often, but all these sort of have their own part to play. But I find that these two tend to be your best friend when you're dealing with logarithms and those types of analytical proofs. Okay, so that's all I have to really say about logarithms. Bam! Isn't that nice?